This video covers a mass spectrometer. So in this section, we're going to be combining a lot of different things, stuff that we've talked about before in electrostatics and stuff that we're talking about now in magnetism. So first off, here we're looking at two separate plates. You have a positive plate and a negative plate. So we know that there's going to be an electric field in between these two plates. That electric field is going to cause a force on a positive charge that goes downward. So we know that if this is the force that's acting on it, then it's going to cause projectile motion. So if this were the only field, then this would be the only force acting on it, and this would be the motion of that particle. But we also have magnetism. So here we also have a magnetic field, and here it's going into the page. So using the right-hand rules, we see that we're going to have a force provided by the magnetic field going upwards. So if this was the only force acting on it, then it would follow this green path instead. But what's happening is both of these fields are actually interacting. So if both of these fields are acting on it, then both of these forces are acting on it. And if both of these forces are equal in magnitude, then my forces are going to cancel out, and then my object's going to move at a constant speed right through both of these electric fields and magnetic fields. So again, the most important thing to take away from this is that my fields are not equal. What we're looking at are the forces. The forces are going to be equal if it moves at a constant speed right through these two magnetic and electric fields. So if the forces are equal, remember that our electric force is represented by QE, and our magnetic force is represented by QVB. That means my charge is going to cancel out, so it doesn't really matter the direction of the charge of my particle. But then we're going to see this relationship that my electric field is going to be equal to the speed that it's moving at in my magnetic field. So we're going to do the first one together, and then we're going to go through the other three so that you can practice determining the direction of my magnetic field, the direction of the magnetic force, and the direction of my electric force. So we're going to be labeling three different things. FE, electric force, FB, magnetic force, and B, electric field. Now let's go ahead and label this is magnetic field, and this is electric field. We're going to label all of these directions. So again, one of the first things that we want to do is the easiest thing would be to just label the direction of the electric field. So we're going to do this one first. Remember that for my electric field, it always goes from positive to negative. So go ahead and do that for all four plates. So now that I've labeled my electric field, I'm going to go back and label my electric force. Again, for this one, you do need to look at the charged particle. Here, for the first one, it is a proton. So when my proton enters this field, it's going to be repelled by the positive side and attracted to the negative side. So go ahead and do that for all four. So now we have all four electric forces on my charged particles. Now, in order for my object to move straight through this electric field, I have to have a magnetic force, which we're going to label in red, a magnetic force that's opposite but equal to this electric force. So go ahead and label that for all four pictures. So now I have my magnetic field for all four pictures. Again, equal and opposite to my electric force. And then finally, we're going to use our right-hand rule or the left hand, depending on the charge, to find the direction of the magnetic field. Again, your thumb is going to go in the direction of V. Your fingers are going to go in the direction of B, our magnetic field, and then our palm is going to go in the direction of the force. So if we look at the first one, we have our velocity going to the right. Okay, so that's the direction of your thumb. So again, your fingers are now curling around. Okay, this is the direction of your thumb. Now, this next part is you need to make sure that your fingers or your palm, I'm sorry, goes in this direction. So this is the way your palm has to face. And then again, your thumb is pointing out in this direction. So you need to make sure that those two things fit. Don't change one without changing the other. So here you're going to see that your hand is awkward and going down, and that means that your magnetic field is going into the page. Again, this will only come with practice, so go ahead and try the next three. So hopefully you got magnetic fields that follow my pictures here. Again, if you're having trouble, try doing them again or drawing pictures of your own, and then come check with me. Here we're actually going to work backwards. We're given the magnetic field. Again, we're told that these charges are going to go straight through. That means our forces are equal and opposite. And then we're going to be asked to label our electric field as well. Again, first off, we are asked to use our right-hand rule to find the direction of the magnetic force. So again, this is telling me the direction of my magnetic field. This is B, and this is going into the page. And again, my thumb is going to the right. So that means that my force must be going up. If this is my magnetic field, my magnetic force, then I have an electric force going downward. If a positive charge is attracted to the bottom, this must be negative, and then this must be positive. So then the direction of the electric field is from positive to negative. So again, try doing the magnetic force for all three pictures first. Again, your magnetic forces should now look something like my pictures. The direction of your electric force is now equal and opposite. And then if those charges are attracted to those plates, well, then you can figure out the charges on those plates based on that. And then once you know the charges, you can tell the direction of the electric field. So the point of all this is to put it all together in what's called a mass spectrometer. This is a mass spectrometer consists of an electric field, an overlapping electric and magnetic field, and then finally another magnetic field. It is used to identify unknown substances. So this is actually going to come out a lot on your AP exam. You're going to be told that this is a mass spectrometer, and you're just going to be expected to know what one is. Again, a compound is ionized, and its ions are sent through the path as shown. The radius of each ion motion is recorded. This information can be compared to known radii of ions in known substances in order to identify the unknown substance. So again, here we have a picture that's completely blank. All we're given is that we have a battery with a 6 volts, and we know that these horizontal plates are charged, that the green region is a uniform magnetic field. That's going to be this middle piece right here. It's actually my blue region. And then we can see that the path of the charge is shown. So first off, we want to determine the direction of the electric field between the vertical plates. So if we look at our battery, this is a positive because it's longer. This is a negative because it's shorter. So this is positive. This is negative. That means this must be an electron that's passing through these two plates. So the direction of my electric field is to the left, negative. I'll say this is negative x direction. And this is E, electric field. The next part, again, we already identify what this charge is. This must be an electron, or a negative charge. Now we're asked to determine the direction of the magnetic field. Again, this blue shaded area is my magnetic field everywhere. Now we can't really tell what our magnetic field is here in the center of these two plates. We can't really tell at this point, but what we can tell is over here. And this magnetic field is the same as this magnetic field. So if you look at the way that it's curving, in order for it to curve in this direction, I have to have a magnetic force that goes towards it. Again, in our previous videos, we said that this magnetic force causes centripetal or circular motion. So again, we have it going downward or towards the center at all points. Okay, so this is my magnetic force at 3 different positions. Again, always towards the center for circular motion. So if you use the right-hand rule, in this case we need to use a left-hand rule because we are dealing with a negative charge. I want you to think about the direction the magnetic field has to have in order for all of this to be true. Again, my palm has to go towards the center of this circle. My palm has to go towards the center of the circle. My thumb has to follow this black line here. That means my magnetic field is going into the page. And if that's true in this area, that's true everywhere. So my magnetic field is into the page or negative z direction. Now we're asked to determine the direction of the electric field. Well, we said that our force has to be going downwards. This is my downward magnetic force. That means I need to have an upward electric force. In order for my negative charge to have an upward electric force, I need to have positive charges here. And I need to have negative charges down here. So now I can see that my electric field is going to go from positive to negative, or up to down. So again, this is a negative y direction. So now I can do the math that goes with all of it. First off, we're asked to determine the speed of the charge exiting the hole in the vertical plates. Again, we've seen this before when we did electrostatics. The speed. Remember, this capital V is potential. And this fancy V is velocity or speed, because this is a energy equation. Remember, this is the energy, this is potential energy on the left-hand side, and this is kinetic energy on the right-hand side. Again, at this point, you can go ahead and just plug in all of your numbers. You should get a value of 1.45 times 10 to the 6th meters per second. Now, in this middle part, we're asked to determine the strength of the magnetic field in the blue region. Again, the first equation that we saw at the very beginning of this section, all we know is that the horizontal plates produce this particular electric field. So if I know the speed that it's moving at when it leaves the first set of plates, then I can use this equation to help me solve for the strength of the magnetic field. So that it's 30 Newton per Coulomb. And again, the speed it had at the beginning was 1.45 times 10 to the 6th meters per second. And we get a strength of about 2.07 times 10 to the negative 5 Tesla. And then finally, what we did in our last video was we solved for the radius of the curved path shown in the right portion of the diagram. Again, if we know the speed that it's moving at, in which case this is v, we also know the force that causes this particular rotation or circular motion. then we can solve for R. Again, this is a Q, charge, and then you can go ahead and plug in all of your values, and you should get 0.399 meters, or 0.4 will work in this last section. Again, for M, you're using the mass of an electron. For V, you're using the speed that you had at the very beginning. Q is charge, in this case an electron, 1.6 times 10 to the negative 19. And then B is the magnetic field that you solve for. Again, this is just a summary of the equations that we used in each section of this problem.